Okay. So today we will do something which is a very important test. It is known as an inclining test or an inclining experiment. Now this is that is whenever you are constructing a vessel, means really constructing in the shipyard, you will see that you need to add you need to do a couple of experiments once you. So first of all you develop the hull. So once that hull is developed, you need to do stability calculations, means you need to make sure that the stability of the ship is all right for that particular hull. So so there are a couple of experiments. The first one is in fact two important experiments that are conducted are, one is this inclining test, and the next one is actually the resistance and propulsion experiments. Right now of course you won't be knowing about resistance and propulsion, maybe we will just mention a little bit later. Right now the first test, so this is for calculating the resistance of the ship in some particular running condition. Now this is to calculate the stability of the ship, that is called the inclining test. Okay. Now so the purpose of the test is to calculate now the real purpose of the test is to calculate kg, that is the position of the center of gravity of the vessel. So this is the purpose, or let me call it the goal of the test, is to calculate this. But what we calculate in this experiment is actually GM. Now what is actually calculated from the experiment is GM, and but the main purpose is to get kg. How do you get kg? Kg you get it if you do km minus gm, right, that gives you kg. Therefore the only other thing you need is km. So km comes from hydrostatic data, that we will look into later. So you can get it from hydrostatic curves and hydrostatic data, you will get km, that is actually a property of the ship as such, and so that we will get in some other way. So right now let us assume that we know km, and once you know km you get kg by km minus gm. So what the experiment does is calculate gm. Okay. Therefore two things, when writing about inclining experiment you need to write two things. The main goal of the test, the test is really done to calculate kg, but what we really calculate using the experiment is gm, and from it it's derived, from the use of km we derive kg. So this is the inclining test. Now let us explain what the test is. That is, suppose you have this is your vessel cross section. Now what we are going to do is, this is the center line, let's that is, suppose there is a weight here of small weight small w. So there is a small weight there of weight small w, and what you do is you hang from this point, some point here O, we hang a pendulum. So the pendulum will remain like this, right, means when you hang a pendulum it always hangs vertical. If it is not moving it will always hang in a vertical direction. So pendulum will be hanging like this. Now what we do is, this weight small w is shifted to the right side here. Therefore what has happened, there is a shift in the center of gravity. When you move a weight here it will incline like this. Okay. So it will incline, let us call this to be the initial water line W0 L0, and this to be the final water line W1 L1. Now as a result of this inclining and it will come to rest at such a point that let us call this G1. It is initially, this is G0, G1, and this is B1, and let us say B0 is here. Okay. This is M. Now, the position is that initially the ship is at an upright condition when the weight is on the left side. Now, the weight is moved to the right, as a result of which the ship sinks on that side, and as a result the center of gravity shifts to G1, the center of buoyancy shifts to B1, and you have the M, as you have seen, the meta center. Now, how will the pendulum look? Actually, the pendulum will still hang vertically to the new position. It will still hang vertically. So, it will be hanging like this. Okay. This is the vertical. From O it will be hanging vertical. Let us assume this is the vertical. So, pendulum will be hanging like this. So, pendulum remains there. Now, what is the distance through which the center of gravity of the ship has shifted? G0, G1. This is again the same formula we have used many times. Okay. Where d is the distance through which the weight has been shifted, this distance, small d is the distance through which the weight has been shifted, and therefore, G0, G1, this distance will be given by W into d by capital W. Now, what you can see here is the angle of heel, this will be equal to phi. Okay, the angle of heel, this is equal to phi. Now, this is just geometry, this is equal to phi. As a result, this will be equal to phi, this will also be equal to phi. It is very obvious, it is, one is horizontal, one is vertical. So, the angles are just same. So, angle of heel is equal to phi. Now, you will see that the two triangles, this triangle G0, that is the triangle G0 M G1, there is one triangle G0 M G1, and there is this triangle, let me call this P and let us call this Q, and triangle OPQ is the two triangle. One is the triangle created due to the G, one is, that is M G and G1, G0 and G1, that is a small triangle. The other one is a triangle created due to the, where the pendulum is suspended, the hanging of that bob and the final position of that. So, there is a triangle produced by that. Now, this triangle and the other triangle will be similar, because the angles phi are same, the other angle is 90 degree and the third angle is 90 minus phi, all angles are same in both the triangles. So, they are similar. Therefore, we can say that G0 M by G0 G1 is equal to G0 M, it is equal to OP by PQ. Okay. It is just the similarity. Therefore, G0 M is equal to G0 G1 into OP by PQ. Okay. Now, G0 M is equal to W into D by capital W into OP by PQ, right. So, I have just replaced G0 G1 by that new value. Now, this is, now what do you have? You are actually having a pendulum. So, the experiment is this, you have hung a pendulum that is at some point on the ship, somewhere inside the ship, or you can hang it from the deck of the ship. Okay. You can hang the pendulum there, sometimes they hang it outside, it does not matter. That what matters is that angle, means the ratio of these two, OP to PQ is what matters. OP to PQ is basically, I think, tan phi. So, or is it cot phi, maybe one of those, it basically depends on phi. So, it is that phi that you are actually measuring. So, now what, so how do you do it? You, OP is actually the length of that the thread in which you are hanging the pendulum. So, that you take a thread of known length. So, you hang a bob at the end, you hang it there. So, this distance is known, and when it tilts, you find out how much this distance is moving. You measure it using, using some calipers, you measure it. So, what you have is actually a model. So, it is not a huge ship, you most likely do it in a model. So, you actually that probably you don't know. There is something called, we call this, that is in naval architecture, actually in same as in aerospace, you do not do the whole experiment in the whole ship. The size of the ship is huge. It's probably 250 meters long. It's an oil tanker, if it is an oil tanker like that. Now, so what we do is we do we take a model which is of a smaller size, but there are some criterion that you do. It's an actual replica of that ship. So that means things like L by B, B by T, or B by D, where D is the depth of the ship. Such things will be the same for the prototype and the model. Prototype means the whole ship. The real ship is called a prototype, and the small one you create in the lab is called a model. So the model is made such that the ratio of those, the ratio of some lot of factors. In fact, in our next class, that is marine hydrodynamics, today we probably will be doing with such, these are known as similarity rules. So it so happens that that class also we will be doing with this today. Similarity laws, it's called, or similarity rules. Means you try, you say that some factors should be similar between the ship and the model. You cannot make a arbitrary model, that's obviously not nonsense. So some ratios you keep to be equal between the ship and the model, and this is called model testing. So this experiment is mostly done using a model. So it's like if you have gone to your towing tank in the department, I mean in our department there is a towing tank, this test is conducted usually. So inclining experiment is done for the industry, they do it. So you make a model of the ship. So you have the ship, you make an exact replica, you make a model, and in this model somewhere you hang a pendulum. You can hang a pendulum of known length, and you measure the distance through which the pendulum has moved. That is using some calipers, you can measure it exactly. Therefore you have two things, this length also you have, this length also you have. Therefore you have the angle that the pendulum makes with the vertical when it is inclined, or in according to this derivation you will have OP by PQ. Okay. So once you have this, and another thing you need is the weight that is moved, this small w. So what you do is you take a known weight. Actually the way in which it is done is there are weights, you have seen in a measuring, you put weights on right side and the material on the left side, like that you do. So those weights are there, like 50 gram, 100 gram, 150 gram. So what inclining experiment is done in this way. So first you hang this bob, you put a 50 gram on left side, and this 50 gram is slowly moved to the right side, and you find the inclining, you find OP by PQ, you find small w, and you should know the distance through which you are moving that small mass, and you should know the weight of the ship, of course, that is important. So once you have those things, you will get G0m. It's not usually done for one mass, you will do it like this, 50 gram, 100 gram, 150 gram, you do a lot and you take an average. So that you will get a fairly rough value of Gm, you will get G0m properly. And once you get so this is the inclining experiment, and this is the purpose of the inclining experiment, to get G0m, but the real goal is to finally find Kg, which comes from Km minus Gm, this formula. Now Km is not calculated using inclining experiment, that is calculated using something else, and you use Gm from here to calculate Kg. So this is the inclining experiment, and it's a very famous experiment, and again as I said, people are likely to ask you this in what is the inclining experiment. You are supposed to know this, that name is very important, inclining experiment, that, or inclining test, that name is very important. Now, and one more thing is that, one more important point here is that when you are doing the ship, when you are doing this inclining experiment, you are actually finding Kg of the light ship. Means when you keep adding weights, for example in the real ship, without oil, let us say if it is an oil tanker, without any oil, without any ballast water, anything, without, that is just the light ship weight. I think I have mentioned to you what is light ship weight, the way it is called a light ship, and plus you have added weights, this gives you the total weight, and the word used for this added weight is actually dead weight. Okay. So you have a light weight of the ship and dead weight. Dead weight is a material that you have added, and you get the total weight after that as a summation of these two. So this inclining experiment is an experiment done for light ship, so you do not have anything else on it. So the, okay, so this is the light ship weight. So these are some of the conditions, that is the vessel should be in a light condition. So, there is no weight on it, and next point is that you again this word you probably don't know, that is you can have moorings. There is a word called moorings. The meaning is that suppose you have a ship like this, suppose if it is connected, let us say this is the seabed, if you connect it like this, in some cases you do that. For example, some ship you do not want to move, you connect it through moorings. The word for this is moorings. So, the other condition for that is you do not have moorings in this, the ship is in a free condition, nothing else. That is, it is very important when you are doing this experiment, you should not have waves and all that, okay, because it is very important. If you have waves, your results it will incline much more than what this predicts. So, it should be a absolutely calm water like you have in your towing tank, do not move anything, no ship should be moving there, no body should be moving there. So, this model is put in a exactly still water, and then you hang the weight, you move this small weight, you see the inclining, you measure this, this distance through which the weight has moved, and you get GM. Then, so this is an important condition, that is there should be no waves, which implies that there should be no wind, there should be no current, the water current should not be there, there should be no wind. Then okay, then these are the different points. Okay. All right, now let us do a problem that will explain this. Okay, you are told that an inclining experiment is carried out on a vessel completing fitting out. Fitting out means it is being constructed. Okay, it is called fitting is a part of it. So, the final part of it, its fitting is being done, and you are doing the inclining experiment. Now, you are given the following data. You are given the displacement of the ship, which is your capital W, you are given the displacement, then you are given small w, the mass of the inclining weight, then you are given small d, the distance through which that small mass is translated. Then you are told, okay, I will just write this. The meaning of this is length of plumb lines means it is actually the length of the pendulum. Okay, plumb line that indicates the pendulum that is being hung there, that is given. Now, to be exact, you need to have one more thing which this problem does. Now, you are given the kg of the inclining weight, which means what exactly is it? This means that when you are doing this kg, for instance, I explained this, when you are doing this kg, you will actually be including the kg of this weight that is translated. Okay. Now, if you want to remove that weight and find just the weight of the light ship, which is what really the kg, which is really the GM that we should be giving as a result of inclining test, you need to subtract another kg, that is a kg of that inclining weight alone or that shifting weight alone. So, kg of that okay, inclining weight is not the hanging weight. Okay, it does not matter how much weight you hang, inclining weight means the weight that is shifted. So, inclining weight, you are given the kg of the inclining weight, and from km is given, otherwise you cannot do kg, you cannot get kg. Km is got from hydrostatic scales. I will explain later what it is. Probably in the next lecture we will be starting with hydrostatic curves. So, km from the hydrostatic scales, you will get it as something that is also given. So, these are the data given. Now, based on this, you are asked to find kg of the light ship. Okay. This is, in fact, this will be how your problem will be set up. This is what you are supposed to do in a inclining test. Okay. Now, once you have this, so let us write the formulas. You know that Gm divided by G0 G1 is equal to, we have given it OP by PQ, which is equal to implies Gm is equal to G0 G1 into OP by PQ, that is equal to W into D divided by capital W into OP by PQ. Now, OP by PQ you can find. Now, you are told, so you are given these two things. okay, I didn't write this actually. There is one more data given. It is the mean deflection of the plumb lines. Okay, this is given. So now what are the, what does it so what do we need to do this? What is OP by PQ? OP is the height of the pendulum, which means which is the length of the plumb line. So that you will put here, and divided by PQ is the deflection of the pendulum, which is the distance, which is the called as deflection of the plumb lines they have written. So that you put here. You are given W, which is the weight of the inclining mass. This is the distance through which the inclining mass is translated, and this is the displacement of the ship. So once you have these things, you will get GM. So you get GM from this. Now you get kg from as using km minus GM. Now what we could do is, in reality the thing is, this small w is so much smaller than the displacement of the ship that really it does not matter what is the kg of, there is no difference in the kg of the ship. By the, like, the ship weight of this whole ship might be, let us say 5 kilograms, or means the model I am saying, the whole ship will be many tons, that is different. Let us say this itself causes, weight of it is probably 5 kilograms, we are adding some 50 grams, it makes no difference really to find out the kg, but to be accurate in this we will do this. Now you know, you have the whole ship with a kg of this, you have a small weight with a kg of that. What will be the light ship weight? It is this concept, it is the final kg. It will be minus kg of that small weight into the weight of that small mass divided by the total. Okay. That will give you the no, it should actually be delta minus W. Okay, you are right, correct. It should be delta minus W. So it is the weight of this. So this will give you the light ship weight. I mean, this will give you the light ship kg. So this, it does not matter even if you do not do this, but this is how you calculate the kg of the vessel, light ship. So this is this problem. Then there is another small problem. This also you will do just to indicate one point, that is the problem is very similar. Yeah.
What was the U in the previous problem?
U. Where is U? Okay, now okay, the problem says this, that is you are told that some weight or timber is moved from something weighing 8 tons is moved from 8 tons with some kg. So this is the weight that is moved, it has a kg of something, and it is moved at distance of 16 meters to one side of the ship, or moved from one side of the ship to another, and as a result of it the ship heels by 1 degree. Okay, because the weight of 8 tons is moved from one side of the ship to another side of the ship. You are given some details of that weight, kg of that weight, and the distance through which it is moved is given, and because of this the ship heels by an angle of 1 degree, inclines the vessel by 1 degree. Now km is given, and you are given the total displacement of the ship. Okay. Then you are asked to find kg of the vessel. Now how do you find GM? In this case let us use the same formula, G0 G1 into OP by PQ. Note one thing, what we are having is actually OP by PQ. What is it? It is actually tan cot phi. Okay. So I mean we can assume tan phi, this is very small angle, 1 degree is very small. So tan phi is like phi, so cot phi is also like phi. Okay. 1 by 5. So it's like 1 by 5. So this becomes, so you can assume this to be g0 g1 into 1 by 5. So the only thing, so what is phi? Phi is given, it's inclined by 1 degree. So 1 degree is your phi. Of course, you have to change it into radians, you have to remember that, and that is pi radians is equal to 180 degrees. So 1 degree is equal to pi by 180 radians. Okay. So this you have to do, you have to convert it to radians. So that's all. g0 g1 by phi gm, and so you have gm equals wd by w phi. That's all. I mean, it's just written in a different format. That means instead of giving the length of the pendulum and the deflection of the pendulum, you are given that this divided by this completely, this angle itself is given. Because why is it same? It's because if the ship is heeled through phi, the pendulum will hang always vertical. Okay. So that angle will be the exactly phi only, you have to know. Okay. Because if this is heeled through phi, this will be phi from the vertical, this will also be phi, as you can see from this figure. So this is initially here, this is heeled through phi. Now this is the center, let us say the pendulum is hanged here, it is hanging like this initially, and now it is hanging like this. This and this will be phi. So if this is phi, this will be phi, and once you have phi, you just have tan phi is equal to the length through which the pendulum has deflected, not the length of the pendulum, it is the deflection of the pendulum divided by the length of the pendulum. So this is just slightly different, just to know how to do it. Okay, then all right, now next one, a very small point, but just note this, that is the implication of this I will tell you. That is again, suppose you have a ship in a condition, upright condition, and something causes it to roll. Roll means we have said it is a dynamic condition, it just keeps going like this. Now you can do one thing, you can actually consider the ship to be moving in a simple harmonic motion, and you know, just like a pendulum oscillating, you can assume this oscillates like this, and you can get an expression for the time period of this roll. Okay. Now you will see that the time period of roll is just remember this formula. I mean, we are not deriving it, so just remember this, the time period of this roll will become 2 pi into k by root, that k is known as, I think you will know this, the word is radius of gyration or gyration, radius of gyration, and it is defined as I is equal to mk square. I mean, okay, I mean you would have done this. So this is known as the radius of gyration of the ship. I, remember, is the moment of inertia of the water plane area about the longitudinal axis. I keep repeating this because it is very important. So this I, so this, if you say this is the length of the ship, we are talking about I about this longitudinal axis, this axis, about this axis, this is the longitudinal moment of inertia, this is the moment of inertia about the longitudinal axis, and of the water plane area, this is I. Now this is given by m is the mass of the ship into k square, that will give you the radius of gyration of that ship for that particular water line. So you get k, and once you have k, you substitute here, you will get T is equal to 2 pi k by this thing. Okay. Now from our definitions of stability, from our derivations of stability so far, we have said many times, I have said many times that GM should be as large as possible, right. That is, I said that GM should be, of course, the minimum condition is that GM should be greater than 0. The more you have, the more stable it becomes. Okay. That is the general law, that is the general principle. Now, so you might think the best thing is obviously to keep on increasing GM by some way. You, for example, you can move weights to the bottom, all the weights you keep pushing to the bottom of the ship, and everything, the top part remains empty, relatively empty, and you will get G at the very bottom. The G of the ship will come down because all the weights are shifted down. If that happens, now is that good or bad? Just look at this equation, this expression for time period. This says that if GM increases very high, time period keeps decreasing, right? It's inversely proportional to root GM. Therefore, if you keep increasing GM, the time period keeps reducing. What does it mean if the time period is reducing? It's moving like this. Okay, if you keep increasing the time period, it will move like this. You won't probably might not feel it because it's very slow. But if it is very high time period, it moves like this rapidly. It's obviously very uncomfortable. Of course, it's just a matter of comfort only. It doesn't matter. It doesn't capsize or anything, but it will just keep moving like this, and you are not comfortable on the ship. So that is why that seasickness and all that comes. So you cannot. So from this we see that you really cannot increase GM very high, but of course you cannot reduce GM either. So somewhere they drew a optimization. So somewhere that optimum value is there where this is also okay and stability is also okay. So this is actually another question like they keep asking in the interviews. First thing they will ask is what is the condition for stability and how do you design the ship so that the ship is very stable. The answer is GM should be made as high as possible. That is the condition. Then the question is, can you keep increasing the GM to any value? Means let's suppose you increase the GM to the depth of the ship almost, or even greater than that. Means you keep increasing M outside, and if G is inside, can you keep doing that? So your answer is no, because of this this time period problem or this rolling problem, you cannot keep increasing GM infinitely, but somewhere you draw a line and you decide this is the optimum GM. So this is, I mentioned this, that is you cannot increase GM infinitely, and this is the reason for it. So this is the this is the straightforward problem. You are asked to find the GM of a vessel or kg of a vessel, provided you are given all these factors: radius of gyration, you are given the time period, and that's all. And once you have that, you can find the GM of the vessel, and from GM you use Km, and so first you get GM from the time period. These are all straightforward problems you can very easily solve. Kg you get it as from this two. Then the next one, I think you can do this also very easily. Okay, now there is one more problem here. Okay, I think this is all right. Now we'll have to going into the next section actually, that is known as the hydrostatic. We are going to hydrostatic curves. What are known as hydrostatic curves? Actually, we are a little ahead of time, so now what do we mean by hydrostatic curves? Okay, first of all, let us define a couple of conditions. What do we mean by hydrostatic data? First of all, now hydrostatic data, primarily you need the principal particulars of the ship. So these terms as we use, it should be clear. Is it principal or principal? I think principal particulars of the ship. So first of all, you should be given the principal particulars of the ship. This includes the length, breadth, depth, draft, CB, and displacement. Okay, so this includes the principal particulars of the, sometimes not the depth, but draft, depth, then CB and displacement. So this roughly represents your principal particulars. So these are the basic things that you need to at least have some make some design of the ship. You cannot design accurately using this, but there are softwares like MaxSurf, it's there in the department also. You can just give these particulars and it will generate a very smooth hull of the ship. So nowadays actually nobody does it by hand, everybody does it in software only. So in fact, given these hull particulars, known as principal particulars, you will get the hull of the ship. Now, hydrostatic data includes one other thing. I have already written, I mean I have already shown you some time back what we called as the offset table, if you remember, right. I mentioned what is offset table. You have water lines, stations, and you have the half breadths, half ordinates. So, something like this, you have the stations here, you have the water lines here, and you will have the half ordinates, that is known as offset table. So, this whole thing together we call as the hydrostatic data. Okay. So, this of course, once you have the offset table, then it is a very simple task to really design the ship, it is very straightforward. Okay. Then now from this hydrostatic data we develop what are known as the hydrostatic curves. It is actually a plot of these. Okay, means different kinds of graphs that indicate variations of different hydrostatic data, mostly with draft. That is the one, that also I will explain. By the way, this is the same. Okay, these two are the same thing. So, you will see it written in both ways, that is the same thing. Now, you usually draw it like this. I mean it can be either way, you can have draft here, we can see it in both ways, and you will have some particular here, and one possibility, very simple possibility, is del, means you find out how much displacement is there below the waterline of the ship for that particular draft, means you are given the draft is some 1 meter, what is the volume below that, that is the displacement. Now, like this you have some curve, and as draft will increase, del should increase. So, it is, let us say some curve you have. So, this is one of the hydrostatic curves. Now, we will develop some actually 4 or 5 types of curves, or you could, but in general it is more common is like this, del is given like this and draft is always given in the y axis. So, this is x and this is y. Draft is mostly given on the y axis because it is just because of convention, means draft is always like this, right, in a vertical direction. So, it looks, from looking at it you can very easily say what is the, means this is one draft, it is 1, 2 draft, 2 meter, 3 meters. So, it is intuitively very easier to understand. So, this is, so from you do this, okay, in our course let us do this, we do not do this, we will just follow that del and draft. Now, these are different types of hydrostatic curves, I mean you can have, instead of del you will have different parameters, we will see. You can have, I do not know if I mentioned it, LCB, LCF, VCB, VCF, then of course, LCG, VCG. So, let me, if since probably I have not mentioned it, the meaning of these things, G is associated with center of gravity, B is associated with center of buoyancy, and F is associated with the center of flotation. Now, what does it each of these mean? Now, gravity, of course, center of gravity, you know, it is the centroid of the weights or the mass. B is the centroid of the immersed volume, okay, the water that is volume that is under, what is the centroid of that volume, that is B, and F is actually what is that, probably I have not mentioned. Now, if you have a water, if you have a ship to some particular draft, on that draft you will have a water plane area. Now, the centroid of that water plane area is known as the center of flotation. It is a very important term, and because the other mostly everybody answers when you are asked, but this one most likely goes away, that is center of flotation is the centroid of the water plane area. So, what will be the Z? So, again these things I will say, LCF mean longitudinal means like this. Now, you know that this direction is called longitudinal, longitudinal means this length, okay. This is known as the longitudinal center of buoyancy, means the x coordinate of the center of buoyancy, from most likely from midship, this is the midship, we call that as 0 usually. In some cases you put the last station as 0 also, we will come to that. Let us call it from midship. So, you have LCB is the longitudinal center of buoyancy, Then you have LCG will be the longitudinal center of gravity, again this length x coordinate of the center of gravity. LCF will be the longitudinal center of flotation, which is the x coordinate of the center of flotation. It will be here, it will be on this line somewhere here, somewhere it will be the centroid of this, right. It will always be on the draft water line, because what is center of flotation again? Center of flotation is the centroid of that water plane area. Water plane area is always on the water line. So, center of flotation is always there. So, the vertical coordinate of the center of flotation will always be the draft. Is it clear? Yeah. So, vertical center of flotation will always be equal to your draft. You can easily see it if you know what is the center of flotation. So, it is the centroid of the water plane area, and you can also have, of course, one more thing, you can call it TCF, transverse center of flotation. It is the distance of the center of flotation from the center line. Means if this is the ship, x coordinate of the center of flotation is the longitudinal center of flotation, y coordinate of the center of flotation is the transverse center of flotation, and the z coordinate of the center of flotation is the vertical center of flotation. So, you have LCF, TCF and VCF. So, three things. Okay. So, LCF is the x, TCF is your y, and VCF is your z, and this will always be your draft, because it is the water plane area's centroid, and the centroid is always on that water plane. Then similarly, you will have all these LCB, TCB and VCB, same thing, longitudinal, transverse and vertical, and similarly LCG, VCG and TCG. Okay, three things, all these things you have to know. Then now among these hydrostatic curves, so among these hydrostatic curves, one curve is slightly important and given a particular name. It is known as a Bongian curve. This is one curve that is slightly important, the other it is very important for some calculations. So, we call it, it is known as a Bongian curve. Bongian curve means you have the okay, you have a now let us suppose you have this ship and this water line. Let us divide it into stations. So, this is divided into different stations, and you take station 0, let us take station 0, and at station 0 suppose you find the sectional area like this, means how should I draw it? Okay, you have a sectional area there, right, sectional area up to the water line. That is actually, that is the meaning of sectional area. I do not have to say about the water line. Sectional area means, so it is like this, your ship is here at one station, any station, let us take the station 0, at station 0 this area means this area up to the water line, not beyond the water line, up to the water line, that area is usually called the sectional area. Okay, that area on, so the shape will be like this, and that area, okay, that whole area, and that area is known as the sectional area. And if you draw a curve, so this curve means you draw like this, let us see how does it look. Actually, it is okay, it is not drawn like that, it is actually a 3-dimensional curve, that is now it is like this. So you will have that is you will draw it such way x from midship means this is all positive, this is the center of the ship. So you will have stations here, this is your last station, this is your last station, means this is your first station, this is your last station. So you will have stations like this. So this is representing the length of your ship, and here you will have it's a 3-dimensional curve in which you will have a curve here which will give you the sectional area as a function of draft. Is it clear? It's not clear. Okay. So first of all, there are 3 coordinates. This is representing x, that is the length x from midship. This is representing draft, and the third direction represents area, sectional area. Okay. Now what you are drawing here is, so at one particular draft, let us say 1 meter. So at that one draft, let us take x some value, this is the first station. So this represents the length. So the ship is lying like this, the ship is lying like this. So these are different stations, and this curve is representing that area up to that particular draft. So what you see is that if you draw a line, let's here let me draw it straight line, means like this. Straight line means, okay, it's a straight line between, let's call this direction, this is x, this is z, and this is y. Okay. Y is actually your sectional area. Now it should, if you draw a line at a particular draft, at let's take one station, let's take this one station, and at this station you draw a line at this particular draft. Let's just draw the z y cross section, and then you will, it will be clear, I think. Z y cross section, what it's showing, so actually it's like this, like the exact ship, you have taken the, a cross section at 1 and you are drawing like this. For different values of z, what will be the sectional area? Means if you have the ship of this height, if this is the draft, if this is your water line, what will be the sectional? It will be this area. Now if it is this, what will be the area? It will be this area. If it is this, it is this area. So with various drafts, you are getting the various values of areas, right? Initially this much area, then this much area, then this much area, it's you are getting different values of areas. So that areas you plot, therefore you get some curve, let's say a curve like this. So as the draft keep increasing, you get increased values of sectional areas. So this is representing your draft versus increased values of sectional areas. Therefore you can do it in this fashion, you can draw a Bongian curve for each station. So this is a Bongian curve for, this is the Bongian curve for station, let us say 0. You will have such Bongian curves for different stations, 1, 2, 3, 4, like that. Different stations will have different Bongian curves depending upon the shape of the ship. So depending upon the shape of the ship, you will have different sectional areas as a function of draft, or this relation between the draft and the sectional areas will be different at different stations, because the ship is not exactly symmetrical from aft to forward. Look, people are looking confused. Is it clear, or should I repeat it? Is it clear? Okay. So this is what we call as a Bongian curve, and therefore you will have Bongian curves for different stations. And if you put everything together, means all the stations also together, it becomes a 3-dimensional graph, okay, between x, draft, and sectional areas. And you can call that also a Bongian curve. That is, it's not a curve, it's actually a 3-dimensional curve. So that so when you are asked Bongian curve, you can say it is a curve. Either way, you can say it's the curve. It's the important thing is that it's the curve between draft and the sectional area for different stations. So you can say you have Bongian curves for different stations. That is probably an easier way to visualize it. So that means you have z y for different x's, x equal to 1, x equal to 2, x equal to 3. You have different Bongian curves. Okay, so this is the concept of Bongian curves. Now let's go into the derivation of hydrostatic data.
So what is the need of this curve?
One thing you can do is to find the displacement, right? No, if you have, let's suppose you are given one particular draft. Now you have the areas at different points, you sum up the area into volume, you will get the draft. So that is one possibility. In fact, that is one of the most important. And what are the moment of inertia, you do not need the sectional area, mainly it is to get the draft, that is probably the main application of this. So, you will get the not draft, the volume displacement, okay, that you can get from sectional areas. In most of your derivations, sectional areas, the volume becomes very important. So, that you can get from Bongine curves. And one of the things is that you, once you make the full ship, you take different sections and you plot it, that is the one of the things too, and you will see different calculations can be done using different curves, like we will do now. We will do some calculations like moment of inertia, longitudinal center of longitudinal moment of inertia, different kinds of moment of inertia, and after that some mathematics to deal with that. You will use these different kinds of curves, hydrostatic curves. Okay. Now, let us go to the mathematics of this. Okay, that is, first of all, there are some notations we are going to follow in the next couple of derivations. First of all, I is representing the station number. I represents the station number. In some cases, we use j also. We will see. I will tell you where it is used, which also represents station number, such that the distance of that station from the 0 becomes j into delta L. Let us suppose that the distance between the two stations is delta L. Therefore, the jth station is at a distance of j delta L from the origin. So, this is how, that is we can use it sometimes. Now, x I is the x coordinate of the station I. Okay. So, x I is the x coordinate of station I. Okay. Then y I is the half breadth of station I, means at station I this distance, if this is the ship, this distance is y I. Okay, then we use something called as alpha I for the Simpson's multiplier. Most likely in this derivations they are using the trapezoidal rule, so it is quite simple. Then we use delta L for the spacing between the stations. And similarly, we say delta T for spacing between different drafts or spacing between water lines. Let us use the correct terms. Now, we have different water lines and the distance between the water lines we call it as delta T. So, these are some of the these are some of the notations we will be using in our following derivations. I will going to keep this away now, you know. Okay, maybe I will stop this class here and we can do this in the next class. All right, thank you.